Watch any classic animated chase. A cat slips on a rug, paws spinning, kicking up a massive cloud of dust as he scrambles to catch a mouse darting across the living room. It looks like pure, unpredictable chaos. But beneath the slapstick energy and flying furniture, every physical movement on screen follows a rigid, predictable logic. This formula maps that movement onto a coordinate plane, the linear equation in slope-intercept form. The variables correspond to physical reality. X measures the relentless forward march of time, while Y tracks the total distance covered from the starting line. The remaining characters define the runner. M is their speed, the rate at which their position changes, and B pins down their exact starting position. By stripping away the animation and translating a character's physical traits into this mathematical skeleton, we can calculate the final outcome before the chase even begins. Take the mouse. Knowing he needs a head start, he begins the chase 10 centimeters away from his hole. Once the chase begins, he maintains a steady, consistent running speed of 2 centimeters per second. When we assemble those physical facts, we get this equation for the mouse. Y equals 2x plus 10. The predator, meanwhile, starts from 0. The cat begins right at the mouse hole with no head start. But he is faster. To close the gap, the cat sprints at a pace of 4 centimeters per second. Putting those traits together gives us the cat-specific equation, y equals 4x. We now have the exact mathematical profiles of our two characters. This is the foundational data we need to simulate the pursuit. The question is no longer about who is faster, but a matter of geography. When and where does the predator finally reach the prey? A catch requires a very specific physical condition. It only happens when both characters occupy the exact same distance at the exact same time. By setting the equations equal to each other, we create a system where the only solution is their point of contact. To solve for time, we subtract the mouse's speed from both sides. Then we divide the remaining head start by that speed difference. X equals 5. The cat reaches the mouse's position exactly 5 seconds after the chase begins. To find the location of that impact, we take that 5-second time frame and plug it back into the cat's speed equation. 4 times 5 is 20. The chase ends exactly 20 centimeters away from the starting hole. Through basic algebra, the physical conclusion of the chase is no longer a mystery. We have calculated the exact coordinates of the collision, 5 seconds in at a distance of 20 centimeters. We can take this algebra and turn it into visual geometry by plotting these mathematical profiles onto a Cartesian graph. This graph tracks their paths. The mouse's line starts at 10 and climbs slowly. The cat's line starts at 0 and climbs steeply until they cross. That intersection represents one unique solution. The physical capture is a mathematical certainty. But what if the variables change? Imagine a scenario where both run at the exact same speed, but the mouse still starts with a lead. This creates a system with no solution. The two lines are perfectly parallel. Because their rates of change are identical, the characters will stay exactly 10 centimeters apart forever. Finally, imagine a scenario where both characters start in the exact same spot at the hole and run at the exact same speed. This produces a graph with infinite solutions. The lines are stacked directly on top of one another, meaning the characters are in physical contact at every single moment of the timeline. Mathematics is more than just a classroom exercise. It is a tool for describing the physical world, turning the seemingly chaotic movement of time, space, and speed into a predictable set of rules.